layer is nothing but the width of web, that is the small b. So if you proceed further, width of the section is the small b. Here AY bar is divided into the two parts. First, AY bar is nothing but the moment of the shaded area about the neutral axis. Here it is nothing but the moment of the flange area about the neutral axis plus moment of the shaded area of web about neutral axis. It combines the two different moments from the neutral axis. So if you proceed further, we know that the moment, that is nothing but the product of area multiplied by the perpendicular distance. Now available area is b bracket d by 2 minus d by 2. How it will be taken? This one, let us refer a particular figure on the tabletop. So if you are referring a figure, I will draw an enlarged figure for your reference. This is my neutral axis. This is the hatched portion that we have to take care into account. This is the value of b. We know this one is d by 2. We know this is a small d by 2. No, this is small b. Also we know y. So I have divided into two parts. This is my first part. This is second part. So the area of the first part is nothing but the b multiplied by this depth. What is the value of this depth? This depth is nothing but d by 2 minus d by 2. And this is the CG. I have to take care the CG to this. So this is my y bar for that. What is y bar for that? It is nothing but half of d by 2 minus d by 2 plus d by 2. This one, it is this value plus this value, and if you are simplifying, this one is equal to half of d by 2 plus d by 2. So if we are referring, because this is the minus sign and half of that, this is the plus sign d by 2, overall it comes half of bracket d by 2 plus, this is a small mathematics, simple mathematics. So if you are referring this thing on this PPT, we get, refer over here, b into d by 2 minus d by 2, this is the area, into half of the capital D by 2 plus small d by 2. This is y bar, and this is nothing but the moment of the flange area about the neutral axis. Now next is the moment of the shaded area of the wave about the neutral axis. Let us found out this one over here right now on this tabletop. Now if you are referring on this tabletop, this is the second area, that is this area. It is nothing but width multiplied by depth. It is this depth. The depth is nothing but d by 2 minus y, small d by 2 minus y. So this available to you is, so area of the second part is b multiplied by bracket d by 2 minus y. Now the CG is available over here. For this part, this is my y bar. This y bar is equal to depth, half of the depth, it is nothing but d by 2 minus y, and half of that plus y, and you are simplifying this one, you achieve half of d by 2 plus y. So if you are referring same thing on this PPT, B cross d by 2 minus y area multiply by half of bracket d by 2 plus y. This is the y bar for the second area. So overall total AY bar is equal to the first part, moment of the flange, area about neutral axis, plus moment of the shaded area of the web about neutral axis. Now simplifying this, please check it out. Half common over here, half from here, half from here. It comes 8. So B by 8 bracket capital D minus small d bracket another bracket capital D plus small d. So it comes to be bracket d square capital D square minus small d square plus, now from this B and half goes out of the bracket, d by 2 minus y, d by 2 plus y, it goes to be bracket d square by 4 minus y square. So the shear stress in the web becomes as tau is equal to F A y bar by IB F by IB, which comes out of the bracket capital B by 8 bracket d square minus d square capital D square minus small d square plus B by 2 bracket small d square by 4 minus y square. Here you just see very carefully, see it is instead of capital B, it is small b because the web portion is there. So please bear me about that one. So now visualize over here. This B capital D small d is a constant value for a given section. Only variable parameter is the y. So it is very much clear that the variation of tau with respect to y is parabolic nature. Also the minus sign is there, minus y square is there, hence with the increase of y, the value of tau shear stress goes decreasing. Interesting point, what is the value of tau when it is y is equal to 0? What does mean the y is equal to 0? Y is equal to 0 means it is at the place beneath the flange or at the top of the web. Because if you are referring the figure on this tabletop, refer the figure on the tabletop, the value of y, it is ranging from y from neutral axis, it is value 0 and it reaches over here. Because we have already found out the distribution for a flange. Right now our intention is to find out the variation on the web parameter. So y is equal to 0 means the value at the neutral axis. Y is equal to d by 2 the variation at the bottom of flange or at the top of the web. So if you come to this point, the neutral axis y is equal to 0. Hence the shear stress is maximum. So tau maximum is equal to F divided by I into small b, be careful, small b bracket b by 8 bracket capital D square minus small d square plus b by 2 bracket d square by 4 as y is equal to 0. By simplifying once again, we obtain a very simple single equation in terms of all the physical properties of the I section, that is F by I small b bracket b by capital B by 8 bracket d square minus d square capital D square minus small d square plus b small b d square by 8. This is the variation at the neutral axis where we got the maximum value of shear stress. at the junction of top of the web and the bottom of the flange where y is equal to d by 2. Interesting point. Intention is to find out what will be the variation of the shear stress at the junction of web and the flange. Hence, we have to take y is equal to small d by 2 and we have to replace the value of y is equal to small d by 2 in this equation. So, we got tau is equal to f divided by I small b bracket capital B by 8 bracket small capital D square minus small d square bracket over plus small b by 2 bracket d square by 4 minus d square by 4. So, this term will be abolished because this is 0. Hence, this term will be abolished and we got an equation f is equal to f multiply by capital B bracket d square minus d square by 8I small b. This is equation number 2. Now, if you carefully look it out, our equation number 1, that is the variation of shear stress at the bottom of the flange, we comes from the basic fundamentals by the variation of the shear stress from the flange point of view. Now, when we come to the second part from the web variation, we having an equation number 2 and see both the equations carefully on the PPT. Please refer. Please refer the equation number 1. This is equation number 1. It is nothing but the variation of the shear stress at the bottom of the flange. This equation number 2, variation of the shear stress at the top of the web, which is the same one as the bottom of the flange. So, the shear stress distribution for the web and the flange, which is shown in the figure. The shear stress at the junction of the flange and the web changes abruptly. Second observation. Equation number 1 gives the stress at the junction of the flange and the web when the stress distribution is considered in the flange. But equation number 2 gives the stress at the junction when the stress distribution is considered in the web. From these two equations, it is clear that the stress at the junction changes abruptly from capital F, that is the shear force, by 8I bracket capital D square minus D square to capital B by small b F by 8I capital D square minus small d square. So, please refer the figure. That is the basic things that I would like to explain or elaborate over here. This is my basic I section. This is neutral axis. This is my baseline. From that I have to plot the diagram. 0 over here, parabolic nature is over here, and we got this stress is equal to F divided by 8I bracket D square minus D square. This is the variation. Now, but if we are considered as a web portion, I found out certain different value, and this value is of B F over 8I bracket D square minus D square. A huge value. This is very small value. This is huge value that indicated that the value of shear stress abruptly changes at the junction of flange to the web. Very less shear stress comes under the portion of flange. Very high shear stress when it comes to the web abruptly changes from the small value to the huge value. The same thing will be expressed over here, that the shear stress at the junction of the flange and the web changes abruptly, and that abruptly means from F by 8I bracket D square capital D square minus small d square to B by capital B by small b bracket F by 8I d square minus d square, capital D square minus small d square. And this is my shear stress distribution diagram for I section. Obviously, this is also a parabolic nature for both flanges. This is also a parabolic nature variation, but repeat 2 times because this is abruptly changes. Whatever the value, multiply by capital B by small b. Capital B, that is the width of flange, small b, that is the width of web, and that value, which is very much higher value as far as this section is concerned. So very much lesser stress, shear stress come across the flange, very much high stress come across the web. So let us wind up to today's session is concerned. So in case of today's session, we learnt up till now the variation of shear stress for circular section as well as the I section. The more numericals related to the I section we will discuss into the next class. Please read at the room. Find difficulty, let us be discussed in the next class. Thank you.